And now for something a little different. Hello, everybody. I'm Gabriel Somlo. And I want to just quick show of hands, how many of us remember the TV repairmen and TVs and radios coming with full schematics? I remember being in awe at around 5 to 7 years old at the guy across the street. My parents head over and he had this multimeter and the soldering iron and he had the whole schematics to the TV and he knew what was wrong with it and could fix it. Now, in this day and age, we're a little further away. We're not really in Kansas anymore with respect to that. Vendors, startups, and established contractors consider asking for complete full source, full disclosure of how everything they provide works, a bit of a rude question. And there's also this kind of general myth that things are so complex and there's so much specialization and division of labor that no single individual is actually capable of comprehending how an entire computer system, hardware and software, fits together. So I want to use this analogy of field stripping. When you're in the service, you spend a lot of mind share taking apart your weapons and putting them back together and cleaning them. And so this whole thing has the purpose of being able to quickly and under adverse conditions while the enemy is shooting at you, being able to debug your weapon and put it back together and make sure it actually works the way you want it to, when you want it to, and doesn't do anything stupid behind your back when you're not paying attention or when you're being careless. And the problem we're having is that modern weapons systems, which are essentially fancy embedded computers dressed up as in exotic enclosures and with interesting peripherals, are really hard to field strip to acquire that same level of trust. And that's partly because of software, but software is relatively much easier to test and tinker with because it's essentially a non-destructive process. Playing around with hardware is currently a lot harder. Analyzing a microchip involves chemical acid baths and electron microscopy, and generally speaking, once you've figured out that it's an innocent chip and it actually doesn't have any backdoors in it, it is now a pile of sand, so you kind of have to use the one that's not been tested. And so that kind of brings me to, okay, what is the hardware attack surface? And the main problem we're having with hardware is that it's made in these fabrication plants, in these foundries that may be located in interesting geographic locations and may try to insert, and we've actually seen research where 20 transistors and 1 capacitor added to a CPU being fabricated will perpetrate a privilege escalation attack straight into the silicon, even in the presence of presumably perfect software. But aside from that, there's obviously the tool chain, the compiler that turns hardware source code into an actual hardware functioning design that could be malicious. So perfectly clean sources could go in and the malicious design can come out. And then last but not least, we have actual bugs in the source code of the hardware, which may be there on purpose or accidentally, or it's an unknown thing, and examples of those kinds of things are recently Spectre Meltdown and other things like that. So back to field stripping a computer. What is a computer? It's basically a bunch of software running on top of a bunch of hardware, and there's some abstraction layers involved in there, but the interesting thing here is the concept of a self-hosting system. What is a self-hosting system? It's a system that's capable of self-sustaining itself. It has kind of like a ship of Theseus being sailed out on the Mediterranean with no contact with the land, and it has all the know-how and the parts and the materials and tools to rebuild itself while it's floating out there on the ocean. And software is like that. For instance, Linux or BSD, there is a kernel that supports a bunch of system libraries, that supports a compiler that can compile its own sources and those of the system libraries and those of the kernel. And so this thing is a self-sustaining, self-hosting environment that could then be used to further develop other software applications. This thing assumes the hardware is immutable and trustworthy, which is a problem because hardware is not trustworthy. And so the goal of this project is to extend the self-hosting property of a computer system to encompass as much of the hardware layers as possible. And so, quick detour into exactly what does hardware development look like from a software developer's perspective. And essentially, it is source code. It's a program written out in a source language like VHDL or Verilog or other hardware description languages. And then that source code is compiled by an actual piece of software that's a compiler that successively elaborates this thing into graphs of gates and ultimately transistors. And so a graph of transistors is basically masks that get fabricated, etched into silicon. And that process is a lot of physics and material science. It's essentially the 5 megaton tail that wags the chihuahua, basically, when you think about it as a compilation stage. Alternatively, we could turn that design into bit stream that configures a field programmable gate array, which is worth talking about in its own right. You ship a set of masks to a foundry that is malicious. They can figure out where the kernel privilege bit is, for instance, and attack it in silicon. With an FPGA, on the other hand, they have absolutely no idea where you're going to store your register that contains your kernel privilege bit. The trade-off is, well, you get a lot more speed and a lot less power utilization and less area with an ASIC than with an FPGA. And an FPGA is basically kind of like Tinker Toys, kind of like snap circuits for grown-up engineers at the nano scale. Not shown in the picture is a grid of bits in a special piece of memory that's called the bit stream. It tells the grid of snap circuits how to wire itself up and how to talk to its neighbors, basically. And it withholds information from the fabrication plant. It's going to be slower and larger, but for ultra-paranoid applications that don't require a lot of CPU power for embedded systems like SCADA or communications gear, this should be plenty of CPU power for that kind of application. So once we've eliminated the fabrication plant can tinker with our silicon facet of the attack surface, we are left with whether we trust our compilers, hardware compilers in particular, and whether we trust our source code. So if we have a system that runs in the field, and do I have a mouse pointer here? No. But anyway, so the fielded system, how far can we trust that, assuming we have its source code? And we can only trust it as much as the source code and the build tool that turns that source code into the fielded system. So then we have to recurse and look at the sources to the build tools, to the hardware compiler. And this is sort of a turtles all the way down recursion that terminates with the question of whether we could trust the C compiler, which builds everything. And that question has been asked by Ken Thompson of Unix fame. And I have a backup slide, I hope somewhere if we need to talk about it in the Q&A, but there's a process called diverse double compilation by David A. Wheeler, which gives us a high degree of confidence that our C compiler is actually clean and trustworthy. And so we can rebuild the entire system that way and declare that we could trust the fielded system to the same extent we could trust the cumulative bounded set of sources that went into making it, but also its intermediate build tools. And so that allows us to bootstrap a trustworthy computer. I've heard a lot of talk about Cleanroom systems, so this is also that. And we start with a host environment, for instance, x86 running Linux, and we're trying to build a trustworthy computer, which is the target system. The target system will be a RISC-V computer capable of running Linux deployed on top of an FPGA. Why RISC-V? Because there's an open source RISC-V specification out of Berkeley. We'll get to that in a second. But we start by doing this diverse double compilation process to establish that we trust to a high degree of confidence that our C compiler and cross compiler are trustworthy. And then we build from source code the compiler, the hardware compiler toolchain. And we build it both natively on the host system and cross-compile it for target environment. Then we cross-compile a software stack, which is a kernel, system libraries, utilities, C compiler for the target RISC-V environment. We build with our HDL trustworthy toolchain the bit stream that's going to turn our FPGA dev board into a RISC-V computer. And then we put all that together, boot it up, and we have a clean room that is trustworthy, and we could be confident that it's going to honestly compile its own components and also whatever other code, hardware or software we import into it from this point forward. And so the current proof of concept, so basically what I'm essentially trying to do here is turn what is traditionally a supply chain problem, how much do we trust Xilinx or Intel, and where do they hire their people from, and where do they do development, into a source code analysis problem. And here's the list of ingredients, the source code that went into everything. We start with actual hardware. There's a Lattice ECP5 FPGA that is completely openly programmable with free open source tools. The free open source tools are Yosis, Trellis, and Place and Route. They're basically software on GitHub that's been developed by various people from universities in Europe and in collaboration with people in Toronto and people here in the United States. It's an open source project on GitHub. There's the Rocket chip, which is Berkeley's reference design for RISC-V, fully free open source code. And so this Rocket chip I took and I integrated it with a chipset, which has the backend system bus and peripherals for Ethernet and hard drive and memory controller and things like that. That is the LiteX environment. So once I took care of the impedance mismatches between LiteX and the Rocket chip and the toolchain and submitted lots and lots of patches to all these projects, I was able to glue it all together and boot it and run Linux on it. And so there's an actual port of Fedora Linux that's supported by Red Hat. They have a RISC-V 64-bit port, so that thing can actually run on this development board and be used to actually recompile the bit stream for the computer that it's running on top of as it does so. So here's another picture that shows how the computer actually hangs together. The dark blue elements are all compiled together as a bit stream that runs on the FPGA. The light blue connections are the FPGA talking to essentially actual DRAM chips, terminal, Ethernet, hard drive, micro SD card, and so on. And so the LiteX environment is in its own little circle, and it's connected in the bit stream with the Rocket chip out of Berkeley. So these sources go basically Verilog, and then you run the toolchain and you compile it, and it's a Linux-capable computer. So now that we have all that, the idea is, well, it took almost a year to put it all together at high speed. It's not the most efficient thing. Right now it's it's trending toward half the performance of a mid-90s Pentium system. It could be made a lot faster by just kind of eliminating inefficiencies in the way it's duct taped together between the Rocket chip and LiteX and the backend bus, which is 32 bits and should be made 64 bits and so on. We could put this on a much faster FPGA than the ACP5, like a Vertex from Xilinx, once we figure out how to actually program that with open source. So we have a complete self-hosting environment. But in the midterm, now that we have a bounded set of sources that is equivalently trustworthy to the fielded system, we should analyze the source code. And that's something here at the SEI we are competent to do. So the idea would be throw formal methods and code analysis at the cumulative ball of source code and figure out, put a number on just how trustworthy this computer is based on that, instead of worrying about who made it and who they hired and what the design team, where the design team was located, and so on. And so in the long term, I would like it to be no longer a rude question to get complete schematics to systems. So to the effect that anyone could really field strip their weapons system themselves, just like they can do with kinetic weapons today, and trust their computer-based weapons to the same extent and using the same kind of process, which I just described. And so I have a recorded demo of the system actually booting into the Linux kernel at 60 megahertz right now. So I got it to 75 in the meantime, so it's a little faster now. And so what it does is it boots into the Linux kernel. And with that, I want to go to Q&A, and we can talk about any questions you might have.
Thank you. I just had one question. So you mentioned before that the ASIC chips that are more designed for communications systems require, just in general, a higher bandwidth. What is the gap in time from modifying this system to be able to operate, say, on like a 4G or a 3G system for communications?
So this would be an embedded computer, CPU memory, with a Wishbone or AXI backend bus. If you had any kind of hardware peripherals like a radio card that you wanted to be driven by a microcontroller or a computer, we would essentially add that card or that hardware to the backend bus and to drive it. So think about this. Think about a Cisco router, and it has a whole bunch of dedicated network cards, and then it has an embedded MIPS-based computer that drives those cards and tells them what to do, and actually figures out populates the what's it called, the accelerated fast path for the packets beyond the first one, and so on. So this would be a computer that drives some kind of system. And it would be the brains of a radio, which is essentially just a computer driving a bunch of peripherals that do RF. I don't know if that answers the question, but that's okay. And the idea would be that an embedded computer that drives peripherals like that wouldn't necessarily require data center level particle simulation, kind of high performance computing types of CPU power, which would then actually make FPGAs a feasible way to do this. Thank you.